Okay, so we have started the moment of a force, and we have done some questions. We didn't do one part here, which I would like to do, but before that, we'll do few questions similar to what we have done before, and then we do the theory part, which we didn't do last time. So so if you look at your workbook, you have questions to find the moment of a force, and also you have Varignon's theorem. Do you remember this one? That means when you have a force, you can divide the force into components and you can take the moment of the components. That theory, we call that the Varignon's theory. So you are already okay with that. But if you forgotten the name, it is Varignon's theory. And also we discuss about the couples. So when you have forces, same magnitude, opposite direction, and if they are parallel to each other, then we said it is creating a couple moment. So we discuss about the couple moments as well. And also there are some questions for simplification of force couple systems, which that part we didn't do, and we are going to do it today. So we discuss about the moment. Definition of moment is the moment that is the tendency to rotation that we call the moment. Moment is taking about a point. It can take about an axis as well, but you guys are only looking at taking about a point. So moment is a vector. It has a magnitude and a direction. So magnitude can be found force times the perpendicular distance, and this, as I have mentioned, it's always about a point. So you need to mention which point about it is taking. Units are newtons, meters. Direction can be clockwise or counterclockwise. Okay, so this is a simple one. I don't think you were in the class last time, so this one is too simple. I think that's okay. So they're all simple. Okay, let's do this one. Would you like to try Phil first, and then we'll do?
Yeah, all right. Okay.
So we extend the line of action of the force, and we draw a perpendicular line from here. And the moment is about Q, and it is the force times the perpendicular distance. So force is 15 kilonewtons, and distance, how did you find the distance? 1.5 what?
Cos 25.
Okay, now so you have this triangle, and I told you when you go towards the cos side, it is the cos is known side. So if you do look like this, cos will give you this.
Oh, sorry. So it's sine 25.
Okay, so when you put this one in the calculator, I think you get 9.5 kilonewton meters clockwise direction. So direction is important. So if you consider this arrow here, it is going like this. So it is clockwise. That's good. We did all these three we did. So we are going to do that again. Okay. Okay, let's Would you like to try this one?
Okay. Mm. Mm. Is it 3 cos 30 times 5 sin 45?
So here, you can do like this as well.
Okay.
Because this angle is 75.
Yes.
And if you extend the line of action of the force, that is this one. And if you draw a perpendicular line, this is the perpendicular line. This one is this distance here. This distance here is 3. And this is 75. So if you take this 3 sine 75, that is this one.
Okay.
So you can do it like that. If you use think the most easiest way. So that 75, that 75 is not given in the question. I think we can figure it out. So how do you figure it out is, if you draw a line like this, this is if you draw a line like this angle is 45, because that is like an X angle like this. And this one is like, this is 30, this is also 30. So this should be 30. And 45 plus 30 is 75. That's how the 75 came. If you want to use Varignon's theorem, there is nothing wrong with that. That means you can divide this 5 kilonewtons into two forces. Like one is like this.
Yeah.
One is like this. Sorry. One is like this and one is like this, because that is your known angle. Isn't it?
That's right. Yeah.
So if you do that, you can't do in one step, but we still can get the answer. So what we need to do is, this will be your 5 cos 45 and this will be your 5 sine 30 plus 45.
Yes.
Isn't it? And if you extend the line of action of this one, 5 sine 45, that perpendicular distance will be this one here.
Which is 3 cos 30.
Which is 3 cos theta, cos 30.
Yeah.
So you can write it as 5 sine 45 times 3 cos 30. It's in the direction of this direction.
Yeah. Well, that's what I did.
Yes, that's totally fine. Then we do this one, extend this and draw a perpendicular line. That will be 3 cos 30, isn't it? Sorry, 3 sine 30, because it's the opposite side. And it is in the clockwise direction as well. So that one will be 5 cos 45 times 3 sine 30. So if you add these two together, do you still get this number?
Yes.
Okay, so that's also right. Only 2 steps. This is an easy one. Let's do this one as well. Let me check whether we have a hard. Okay, this one is better. Can you try this one, Phil? So I got forces like this, 400 sine 30 in the horizontal direction and 400 cos 30 in the y direction. Okay, let's, then if you extend the horizontal force, the perpendicular distance is 0.2, isn't it?
Yes.
So 0.2 times 400 sine 30. I want you to tell me the direction.
That's counterclockwise.
Yes, that's good. So you are going like this. And how about the other one?
Is 0.4 times 400 cos 30 clockwise.
That's right. Yeah, you have understood it. So when you add these two together, we get the answer, which is 98.6. Is that right?
Sure. Yep.
Okay. Okay, so I think you are okay with the moment.
Yes. Yeah.
Yeah. So that's good. So when you have this kind of a one, remember the thickness of the beam is important here. See, you are asking about O, moment about O, then it is like this. So this force is not going through O, it has a 0.5 distance. In some cases, they are saying the thickness of the beam, ignore the thickness of the beam. In that case, you can consider this is as 0. But if they say the thickness of the beam, consider it, then you need to consider it as a number, then you get a force moment, a small moment because of this one as well. Okay, so that one is fine. That one is Are you okay with when this one is not given, when the angle is not given, are you okay to divide it into two forces?
Yeah, just using the 3-4-5 rule.
Yes, so 3/5 here because this one is 3, this one is 100 times 4/5. And the other thing you need to remember is don't divide it like this, divide it where it is touching the object. Otherwise, it is hard for you to take the perpendicular distances. So that's okay. This one is this is a good one. Can I give you a chance to do?
Okay. Yep.
And then we'll move to the other topic, couples. Okay. Here, problem is with taking the perpendicular distances.
Yes. So it's 0.9 cos 45 minus 0.3 plus 1.2, I think.
That's right. Yes, that's right. So that will be 0.5 meters. 1.5. This is my... Are you okay with this? So would you like me to do this one?
No, I think I can manage that.
Yeah, I'll put this PowerPoint anyway in this. So later on, if you feel like you've forgotten, you can.
Mhm.
All of these ones are complicated in taking the distances. That's all. The one will be like this. One force will be like this. So that is your perpendicular distance for that. And the other one will be like this. So perpendicular distance is that. So you have to divide this 200. This side it will be cos 45. This side it will be sin 45. 45 is doesn't matter. Sin or cos, you get the same answer, but still it's good to follow the same method. Okay, now let's go to the moment of a force couples. This one we did that day. I hope you remember 200. We got 204.
Yep.
This one also we did. This one we did as well. Did we? Yes, we did. This one also we did. Okay, let's do this one. Would you like to try, Phil?
Okay. Triangle plate. Okay.
They are couples, so you don't have to worry about around
Yeah.
one. Yes, so you can consider these as a one. So,
What is that? Clockwise. That's one.
so we get 200 times 0.4. We have 150 times 0.4. 300 times 0.4. Now we need to know the directions.
Well, they're all counterclockwise, aren't they?
Counterclockwise, counterclockwise, counterclockwise. Yes, so you add all together, your resultant also is counterclockwise.
60 or something. You think all up counterclockwise?
Yeah, that's right. This is again same.
No, it's another couple. Oh,
This one is one moment or one, and this is the other. Okay, so I think couples also fine, isn't it?
yes.
Okay, we'll move to the new part, new section. Simplification of force couple systems. It's the important part. So simplification means when you have many forces and moments applied on a structure, we should be able to put them into one force and a moment. So we can solve this, simplify this into a one force and a moment at a certain point. So that's what we are going to do. So let's see how we do it. So for example, let's take this one. We need to know how to move things to a one place. So here, this F1 is acting at this point. F2 is acting on this point. Moment is acting at the end. So if you want to bring everything to the P, we need to know one by one how to do it. So let's see how to do a simple one. So let's take, you have just 500 here. And we need to bring that to A. So we can't do any changes like, the final effect, net effect should be this. Now, if I do like this, if I do like this, tell me, if I just apply another 500 here and another 500 here, have I done anything to the structure? Or
No, they balance out.
it is canceling out, isn't it?
Yes.
So this is the same structure that I had with the same forces. Nothing, I haven't done anything, any effect. I haven't created any effect. So now if you consider this, what is it?
It's 500 times 5. What's that? 2,500?
2,500 couple moment, isn't it?
Yes.
Yes, so instead of having this one, can't I do like this? Can I have this 500 and can I have a couple moment of 2,500 Newton meters? Can I do that? I can. Why is that? A couple moment, it doesn't matter where it is acting. It creates the same moment about any point.
Okay.
It's okay to make this a couple moment. So I have brought this 500. Now you can see all the forces and moments are in single point. This 500, before we had this. So before we had this. Now without doing anything, I have brought everything to one point, which is at the point A, isn't it?
Okay.
Is that right?
Yes.
Yes. So how we can do it? We don't have to draw and do it again. So whenever you have a force, you can bring that to A, plus you have to find the moment created by this force about A. So if you find the moment created by this force about A, force times the perpendicular distance, which is 2,500, that is the moment comes to here. So without doing anything before that I did, I can, what I can do is I can just bring this 500 to A. This is 500, and I find the moment created by this 500 about A, which is 2,500 Newton meters. So I bring that one as well. So that's what I'm going to do. If you have many forces, you can still do the same thing. One by one force you replace by a force and a moment. If you have another force, that force also you can replace by a force and a moment. So let's do a few questions and see, simple ones. This one we did. This is what we did. Okay. Okay, now we have two. So can you tell me now how to do? Just take one. Just ignore the 200. If you ignore the 200, we have the previous question. So I can do this. Am I right?
Yes. Yep.
Now, if you have just 200, tell me how you're going to do this one. What you're going to do. So you.
It's 200 times 2.5.
Okay, so 200, I'll take it to here. And 200 times 2.5, which is 500.
Yeah, 500. Yeah.
And that 500 moment is which direction?
Counterclockwise.
Yes, so this is what I got. Am I right?
Yeah.
Okay, now we have separated we have separated into two forces, but we need to add them together. Now, how do we add these together? Look at it. Look at this one now. So we have 200 upward, 500 downward. What is the resultant of that?
So 200 up and 500 down is 300 down.
300 down. So we can say 300 down. Now we have moments 500 counterclockwise, 2,500 clockwise. So what is the resultant of that?
So 2,000 counterclockwise.
2,000 counterclockwise. So we don't need to do this. So we can replace this one by this. Make sense?
Yes.
So we add them together. Now we get this. So we got that. So that means this one can be drawn like this. So we simplified it to a single force and a single moment acting at a one point. So that process we call the simplification of force coupled systems. So now how about this one? How can I bring that to A? So if I bring this to A, we do the same thing. 500 is, what is the moment created by this 500?
0.
0. So there is no moment. There is no moment. Just this one, just sliding. So this, when the force is going through the point, we can just slide it. You don't have to consider a moment because it doesn't create any moment. We call this kind of forces sliding forces. So if the force is going through the point, which we need to simplify the system for, you can just slide it. So we slided that one. Okay, so that we call a sliding vector. How about this one now?
So,
You bring it like this, do you?
yeah.
Okay. Now, it's right. Now, how do you find the moment?
5 times 5 times 500 cos 30.
Yes. So you can shift the force, but now you need to find the two components to find the moment. So this is 500 sine 30. This is 500 cos 30. So this one is going through the point. So this one doesn't create any moment. 500 cos 30 is creating a moment, which is 500 cos 30 times 5 in the which direction?
In the clockwise direction.
Clockwise direction. So you can now get rid of all of this, and you can write this as 500 cos 30 times 5 Newton meters. All good?
Yes.
So okay, can I give you a few minutes for you to do this one? You need to make it to a single force, okay? You can take one by one, but finally you need to make it to a single force and a one moment. And they're asking you to bring everything to A, isn't it? A. You have to take everything to A. I'll give you a few minutes.
Okay.
You have altogether 3 forces.
Yeah, so it's 3, 4, 5. So it's so
So this 1000 is really easy. Am I right?
Yeah, there's no zero.
Sliding. Yes. This is 1000 sliding. And this 750 you can take like this. And what is the moment of this one?
0.9 clockwise, 630.
630 Newton meters. And how about the 500?
That one is
What is this theta?
I don't know, but the ratio is 345.
Is it 345?
Yeah, it's
9, 12,
9.
yes.
Yeah, 9 is 3 threes, 12 is 4 threes, so like the 500. So that breaks out into a 300 by 1.2 clockwise and 400 by 1.8 counterclockwise, I think.
Let me check. You are saying, so let me, if you find tan theta 1.2 over 0.9, I'm gonna check whether the ratio and the theta are the same because so tan inverse tan inverse 1.2 which is 53 degrees, 53 point. So you took it like this. This is 4, this is 3, right?
Yes.
So tan inverse 4 over 3. Let me check. Yes. Yeah, you are right. So this is 3, this is 4, and this is 5. Yes.
Yes.
Okay, what did you do now?
I took 300. Well, so yeah, the two forces are 300 and 400.
Yes, so this is 300 and this is 400.
Yeah, so the 400 is, where's the 400? 400 is 1.8 from A.
Yes. So it's making a moment in this direction.
Counterclockwise, yep.
Yes. So that is 400 times
1.8
1.8.
is
Yes.
720, I think.
Okay.
And the other one was 300 times 1.2.
Yes. And it is in the clockwise direction.
Yes.
300 times 1.2.
So it's 360 with the result being 270 clockwise.
Okay. So you have already considered all these ones. That's
Yep.
good. Which is this, and this two.
Yep.
Okay. Now the force. Resultant force. Resultant, I'll delete this moments because now we are okay with the moments. Let's see the resultant force. So let's bring all the forces. So when you bring all the forces, you have 300 this way, and also you have a 400 this way. Am I right?
Okay, yep.
Now, you can't keep it like 4 forces. You need to consider, you need to make it to one force. So how do we make it to one force?
Oh, okay. So you sum of them.
Yes. So these two you can do together. What is it? It is 350, isn't it?
Yep.
And if you do this, it is 700 this way.
Yep. Yep.
Okay, now what we have is, we have 700 this way, and we have 350 this way. We again can't keep like this. Do you remember how we make it to one force? We have 700 and we have 350.
Just with Pythagoras, can't we?
Yes, so the resultant is start to end. So that resultant is equals to 700 squared plus 350 squared, square root of it.
Yeah.
And the angle theta, do you remember tan theta is opposite 350 over 700. So you find the theta as well. So your resultant is going this way. So you need to find the magnitude and the angle theta.
Okay.
So theta is 26.56 I got. Degrees. $782.6. Is that what you get?
Yep. Yeah.
Okay, so we have one force and the moment, what did you say the moment resultant?
Was 270 clockwise.
So we have simplified the system to a single force and a moment acting at a certain point A. Are we good?
Yes.
Oh,
Yeah. So,
that's good. So don't need all this anywhere now because we have already done. So we got, so let's see whether we get the same. Yes, we got the same. I have found the other side angle, but that is 90 minus angle, that is right, which is, so we have made the same thing. 315, how come I got 315? What moment you got?
I got 270. Let's do it again.
So 750 times 0.9.
Yeah.
300 times 1.2.
Yep.
400 times 1.8.
Yeah, that's what I got. Let me just do the
Okay, so
calculator on.
two are clockwise, other one is counterclockwise.
Oh yeah, no, sorry.
Is this right? 315?
Yeah, I just did the wrong one. The first one, 750 by 0.9 wrong somehow. Yeah, so 675 plus 360. That. 675 360 minus. Yeah, 315.
Okay, that's good.
That's not a mistake.
Okay, so that is the simplified version of the same. Okay, this one has the only difference here is you have 200 Newton meter moment here. So it's a couple moment. It doesn't matter where it applies. So you can just bring it to it. Other three forces, you need to follow the method. So 40 will be there. And this 200 I can straight away bring, because this 200 Newton meters, I don't need to do anything because it is a couple moment. It doesn't matter where it applies, we can bring it to anywhere. So that's case. That's just I can bring that to here. This is already here. Now the next one, 30 you can bring. 30 you can bring with a moment of 30 times 3, isn't it? Clockwise.
Yeah, yeah, 30 times 3.
Oh, 30 times 3 is 90. Then this one, 50, we need to divide into 2 directions. So 3, 5, 3, 4, 5, 30 and 40. So 40 is a sliding vector. So we can just bring it. 30, we can bring the 30, and also with the moment of 30 times 6, isn't it?
Yeah, yep.
So 30 times 6 is 180. So these are the things we have. So all the forces are downward, these ones, 30, 40, and 30. When we add those together, 100. And moments, all 3 moments are in the clockwise direction. So 90, 200, and 180, we can add them. So we so what we can do is, here we have 100. Here we have 100. And here we have 40. And moments, we had 200. We had 200 plus 30 times 3 is 90 plus 180. So when we add all these together, that will be our moment. Now we are not finished. We need to combine these two and make the resultant. We need to find the resultant. So that's the same procedure. Only thing is, when you have a moment, you can just bring that moment, and you need to, so we need to add that moment as well. We added it. So that's good. Okay, let's do one more, and then if you are okay, we can move to the next topic. Can I give you a few minutes, Bill?
Yeah, okay.
How are you, Paddy?
Sorry?
Where I was talking to Paddy. Are you there?
Oh,
He just joined, I think.
yeah, okay.
So, Paddy, do you understand what we are doing, or do you want me to go through again? Okay. Do you get something like this, Phil?
Yeah, yeah. So, because
Now, if I consider all the forces in the x direction, it is just one force, which is 900 sine theta. All the forces in y direction, that will be 30 plus 300. Moments, you have 900 plus 30 times 0.75 plus 300 times 2.25 minus 300. So these are the moments. Water. Is that right?
yes.
Okay, so now we can't keep like this. We need to add these two and find the resultant will be in this direction now. So, but you know how to do it now. So let's see. When we add all together, 900 minus 30. So I got the resultant moment as 1034.57. Do you get the same?
Yes.
Okay, 900 sine 30. So force I got 1169.5. Is that right?
Yes.
Okay. And you can find the angle theta. And theta is opposite, which is 900 sine 30 divided by 100 plus 30 plus 300. So you can find the angle as well. And inverse. .22 degrees here, 22.6 degrees. If you did with 90, the side it is 76, sorry, 67. 67 or 23. Is that right?
Yes.
So either if you look at this angle, it is closely 23, and if you look at the other side, it is 27. Sorry, 67. Okay, so we are okay. So everything is the same. Okay, so if you whatever the shape you get, you do that in the same way. So nothing different. Even this one the same. So you can try this. This one again, you have a triple moment, so you need to take that. Okay, so there is a one more thing, we don't have it here. What do you want to do more questions, or is that okay if I go to the next topic?
I think that's fine. I think we can move on to the next one.
Okay.
I mean, I'm all right with that so far.
Okay, now we don't find forces acting as point loads. We can have distributed load. For example, if you consider uh, dead weight, or as the weight of the material, if you have a beam, that weight also, the concrete weight also matters. It is not acting at a single point, it is acting as a distributed load. Again, if you consider the wind load, it is not acting at a certain one point, it is a distributed load. So whenever you have distributed loads, we should be able to make it to a single load acting at a certain point. We should be able to simplify it to a single load acting at a certain point.
Yep.
So, uh, so what we can do is, so you only get two types of distributed loads, but later on you will learn, if you do more studies, you will learn any shape how to do it. So this one we call uniformly distributed load. This part is uniformly distributed load, and the triangular part we call a triangularly distributed load. So that's the only two types that you get in your questions. But there can be loads like this. There can be loads like this. So in that case, you need to do integration. So the total load acting is the area under this curve. So you can find the area under any shape of a curve by using integration, but you are not going to do it here. But if you are interested, you can find questions and answers in that as well. Okay, now let's say in our case, we need to find out we should be able to find out we should be able to find out the single force here. So to find it for uniformly distributed load, that is, you are going to replace this by a single force acting at a certain point. So what you do here is, so they are saying per meter it is 3 kilonewtons. So you consider this area. So this 3 is this height, 3 meters. Sorry, 3 kilonewtons per meter. 3 is this height. So if you times this 3 by 2.4, that will give you the area. So this will be 3 times 2.5 newtons. Sorry, kilonewtons. And for a triangle, it is the same. So if you consider the triangle, you consider this triangle's angle, area. So that will be height times base times the height is 3. So this many kilonewtons are acting on the triangular, from the triangularly distributed load, and this many kilonewtons are acting from the uniformly distributed load. So that's the magnitude. Is that clear, Phil?
Yeah.
Or not? Now we need to know the distance from where it is acting. So it is acting on the centroid. So its centroid of a rectangle is at the middle here. Middle, so that will be 1.2 meters from here.
Yeah.
Isn't it?
Yes.
And in the triangle, if you know the triangle centroid it is close to this big side. So that will be, this one will be 2/3 of the length. So we can now say on this beam, we have half times 1.8 times 3 kilonewtons acting at 3/2 times 1.8 meters.
Yeah.
And another force of 3 times 2.4 is acting on, if you look at from here, that will be 1.8 plus 1.2. So we have two forces acting like this. So this distributed load we have converted to 2-point loads acting at a certain known 2 points. So this one is acting at this many meters away from this A, and the second one is acting this many meters away from A. Is that make sense?
Yes.
Okay, so that's okay. Can you simplify this to see whether you are okay? So always 2/3 is from the tip. Okay, so when you find this one is L/2 acting at a L/2 distance, this one is, if you consider this as L, 2/3 L, the 2/3 is from the tip, not from the other side, from this side. I'll give you a few minutes. So first one is easy. 30 times 3, 90 kilonewtons, isn't it? Acting at 1.5 meters away,
Okay.
isn't it?
Yes.
You can say this one, 90 kilonewtons acting at 1.5 meters away. How about this one? 100 is this. So it's half times base times the height. So that would be
So it's 200 acting at
half times base times the height is 2.5,
oh, not 200, yeah.
isn't it?
Yeah, 5. So 250.
2.5 times 50. 125, isn't it?
Yep.
And acting at where? From the tip, 2/3 times 5. Isn't it?
Yep.
3.33.
Divided by 3.
Okay, are you okay with this?
Yes.
Okay, so this picture will be given to you anyway, even though you have forgotten. So it's not, it can't be forgotten actually, it's very easy to do. This and this and this and this. Area under the curve and 2/3 from the tip for the triangle, other one is at the middle.
Oh.
So this one we already did.
Mhm.
We did this one, isn't it? At the start, we did this. Let's do this one as well. I think after that we are okay.
Which one? The one on the left or both?
Both.
Both. No.
Mm. This one, the last one. Yeah, this is the last one anyway from in the slides. So.
Four. I've done it, I think.
Okay, so did you get this?
Yes.
Okay, next one. Like this.
Yeah, yeah. That was.
So 4 from the tip, always from the tip 2/3. So it should be 2 from this end and the 4 from the other end.
And 4 from the other one, yeah.
Okay.
So it's half times 6 by 3 and half times 6 by 6. Yeah, 18.
Okay, that's it. So that's all we have. Yeah, so that's all we have actually. That's good. So there are some questions we skipped because I felt like you are confident of doing that. But I'll upload this one if anyone else need to get the answers.
Yep.
Yeah, so that's all for this week. And I will make the quiz open and make an announcement as well. Okay, so if you have any question, we can discuss. Otherwise, we can wind up the class and I'll see you next week.